What's up, everybody? This is Mr. Richardson coming at you live through the power of the internet. What we're going to be doing today is continuing our video series on factoring. What you should do at this point is make sure that you've checked out my previous videos. I've posted a bunch of videos on the different types of factoring, and that type of learning is going to be essential to what we do today. If you haven't done it yet, make sure you hit the subscribe button and like this video so that you're available for all future content. Let's jump right into it. First thing we want to do is review the different types of factoring that we've talked about. We've talked about 5 different types of factoring so far, and we want to review those 5 types. Let's name them each and also explain how to identify each method of factoring. Well, the first method of factoring we talked about is greatest common factor. Greatest common factor factoring just means that you factor out any common factors that exist among the terms. This one is very easy to identify because, as the name implies, there are some common factors. For instance, look at this first example here. Here I can see that there's a 2 and a 4 in both terms, so there must be a common factor of 2. When I look at these second terms here in the second example, they all have a variable in them, which means they'll have a variable common factor. So not only can you look for constants, but you can also look for variables as common factoring. After we talked about GCF factoring, we talked about trinomial factoring. Trinomial factoring is very easy to identify because the terms are always in this form, 1x squared plus bx plus c. Of course, they don't have to be plus signs here, they could be minus signs, but the important thing to remember is you have these 3 terms, an x squared term, some type of constant times an x term, and then just a constant, and there's a 1 in front of the x squared, and we know that's always going to factor to this form, this binomial product. The next type of factoring that we looked at was grouping. Factor by grouping involves GCF factoring, so you need to know how to do GCF to do it, and it's very easy to identify. Just look for 4 terms where no common factors exist among the 4 terms. We also looked at factoring by the difference of 2 squares. I'll refer to this as DOTS as an abbreviation. With difference of 2 squares, you need to have 3 things happening in order to identify the difference of 2 squares. You have to have a difference. That's this subtraction sign here. You have to have 2 terms, 1 and 2, and they have to be perfect squares. In order for a variable to be a perfect square, the exponent has to be even, and in order for a constant to be a perfect square, it has to be the result of squaring some number. For instance, 2 squared is 4, 4 squared is 16, 3 squared is 9, so 9 would be a perfect square. And the difference of 2 squares always factors to this form, with a plus and a minus, and you have 2 binomials. The last type of factoring we talked about was slide and divide. Slide and the divide method is pretty simple to identify. When you're looking at slide and divide, it looks very similar to trinomial factoring, except this term in front of the x squared, that coefficient there is anything but 1. So if my a term is 6, -6, 2, -2, even -1, that's going to clue us in to use slide and divide. So those are the 5 methods of factoring that we've talked about so far. Now let's talk about what is factoring completely. When you want to talk about factoring completely, it's factor and completely. So let's talk about what it means to factor. We learned earlier that factor means just to write as a product. Think about the number 8. If I want to write the number 8 as its factors, I could write 4 times 2. I could write 1 times 8. I'm just writing 8 as a product. The same is true with any variable expressions. Completed means to finish something. If you completed a job, you finished the job. Anything that's completed has come to an end or finished. When we want to factor completely, it's just both of those things together. What we're doing is we're going to keep factoring until we've come to an end or till we've finished. Essentially, we're going to be factoring more than one time. So that's what's important to know about factor completely, is you're factoring more than once and you just keep doing it until you're finished. A couple things to note when you factor completely. The first thing is that most of the time that you're factoring completely, you're going to start with GCF factoring. In fact, when you start these problems, I always want to check first, is it possible to take out a GCF? The reason I always do that is because typically we're always going to start with GCF factoring. The second thing to note about factoring completely is that with the exception of the difference of two squares, once a method of factoring is used, it cannot be used again. For example, when we factor completely, we're going to factor more than once, typically 2 times. If I factor GCF to start, I can't use GCF a second time. I use it once and it's finished. If I use, let's say, factor by grouping once, I can't use it a second time. Once I've used it, I can't use it again. The only exception to that rule is with the difference of two squares, which I'm referring to as dots. If you use dots the first time, you can absolutely use it a second time if the situation arises. But that's the only method of factoring that you can use more than once when factoring completely. Let's jump into an example and see what we're talking about. In this first example here, I want to factor this expression completely or factor more than once. First thing I do is look at the structure and decide, can we do GCF factoring, since most of these start with GCF factoring. When I look at this, I can see that both of these two terms have a variable in them, so there's absolutely a variable GCF. The GCF here is always the one with the smallest exponent. Here, between x cubed and 81x, the smallest exponent is just x to the first, or x, so that's going to be my variable GCF. Then I can open up my parentheses, bring down the minus sign, leaving space for two terms, and we divide. X cubed divided by x is going to be x squared. 81x divided by x is just 81. Now I look at the remaining expression here, this piece that's in blue, x squared minus 81, and decide what type of factoring is that. Well, that type of factoring is the difference of two squares, or dots, because I can see I have a difference, I have two terms, and they're perfect squares. This x I'm not going to touch. That part of the expression just comes along for the ride, and I factor this by the difference of two squares, which always factors to a binomial product with a plus and a minus. I take the square root of x squared, which is x, take the square root of 81, which is 9, and we're finished. I factored this completely. I factored it twice. First time with GCF, second time with dots. It cannot be factored anymore. Let's try another one. Here I want to see if I can factor this expression completely. When I look at this, I always start to think, can I use GCF to start? And the answer here is no. If I look at the first term in this expression, there's only variables here. There's no constants. And when I look at the second term, it's just constants. There's no variables. So I can't take out a GCF because one term doesn't have any variables and the other term doesn't have any constants. Looking a little bit closer at this, it couldn't be trinomial. There's not 3 terms. It's not in the right form. And also it can't be grouping because there's not 4 terms. All that's left is dots, the difference of two perfect squares, and I can see that's exactly what this is. I have a difference, I have two terms, and they're both perfect squares. Variable terms will be perfect squares when the exponents are a multiple of 2, something like 2, 4, 6, 8, 10, 12. X to any of those powers would be a perfect square. If this is dots, I have this form here, a binomial product with a plus and a minus, and I take the square root of each. The square root of x to the 4th is x squared. The square root of 16 is 4. And now I have to factor this again because it said factor completely. Well, when I look at this one here, this is the sum of two perfect squares, so that one will not factor. But this one here is the difference of two squares again. Remember what we said, the difference of two squares can happen more than once. So this x squared plus 4 is going to come along for the ride, and I'm just going to factor x squared minus 4. Notice how this piece didn't change. Difference of two squares again has a plus and a minus. The square root of x squared we know is x, and the square root of 4 is 2. I have now factored this completely. This one was a case where I factored by dots the first time, and then again factored by dots the second time. Let's try one on our own. See if you can identify the expression that shows this polynomial factored completely. First thing I want to do is rewrite this expression. When I look at it, I always check to see if I could do GCF factoring. This one absolutely can do GCF factoring. I see that all of these terms are even, and I also see that they all have a variable. So let's first look at the GCF of the numbers. What is the greatest common factor of 2, 14, and 20? In that case, it has to be 2. Let's look at the greatest common factor of x to the 4th, x to the 3rd, and x squared. I'm always going to pick the variable expression with the lowest exponent, which in this case is x squared, making my GCF 2x squared. Open up my parentheses, bring down my minus and plus sign, leave space for 3 terms, and divide. 2x to the 4th divided by 2x squared would just be 1x squared or x squared. 14 divided by 2 is 7. X cubed divided by x squared is x. 20x squared divided by 2x squared will be 10. Now, of course, it said factor completely, so we have to factor again. The GCF piece, the 2x squared part, will just come along for the ride, and I have to factor this piece in blue that remains. Looking at this, it's obvious that it's trinomial factoring. I need 2 terms that multiply to 10 and add to -7. Those 2 terms are -5 and -2. Factoring trinomial factoring always yields a binomial product like this. Notice the 2x squared is still there, and just plug in the pieces that go in the blank. I have now just factored this expression completely. I first used GCF factoring, and then I used trinomial factoring. Let's try another one. See if you can factor this expression completely. First thing I want to do is rewrite the expression. Looking at this piece, it does look a lot like dots, but it can't be. Both of these terms aren't perfect squares. They're not because they both have odd powers for the variable pieces. X to the 3rd is not a perfect square, and either is x because it's really to the 1st power. I always want to check, is there a GCF? There is in this case because they both have variables here, and their GCF is always the smallest variable, it's x. Open my parentheses, bring down the minus sign, leave space for 2 terms, and divide. X to the 3rd divided by x is x squared. 9x divided by x is 9. Look at what type of factoring remains. Now at this point it's the difference of 2 squares, so I can write this binomial product with a plus and a minus. Notice that the GCF of x is still there. It came along for the ride. We know the square root of x squared is x, we know the square root of 9 is 3, and I get this final factorization. Let's try another problem. See if you could factor this expression completely. First thing I want to do is rewrite this expression. At first glance, it may look like trinomial factoring, but I see we have x cubed as the leading term and not x squared, so that won't allow this to be trinomial. And remember, we always want to look for GCF factoring first. When I look at these 3 terms, I can see they're all even, so I know they're going to have a constant greatest common factor, and I can also see that all 3 terms have a variable, so they're also going to have a variable GCF. Well, the GCF of 4, 8, and 32 is just 4. And of x cubed, x squared, and x, we pick the one with the lowest exponent, that's going to be x. Open my parentheses, bring down the plus and minus sign, leave space for 3 terms. Now we divide. 4x cubed divided by 4x is x squared. 8x squared divided by 4x is 2x, and 32x divided by 4x is 8. Leave the GCF alone and see what type of factoring remains. Now I have trinomial factoring, it's in the correct form, so I know it's going to factor like this, where the 4x doesn't go anywhere, and I leave space for 2 binomials in this form. For trinomial factoring, we need 2 terms that multiply to -8 and add to 2. Those 2 terms here are going to be positive 4 and -2, which I just replace in the blanks. Let's see if you can try another one. See if you can factor this expression completely. First thing I want to do is rewrite the expression. Looking at this, I want to see, could I use GCF? And the answer is we can't. The reason we can't use GCF is this term here is just a constant, so no variables could exist as a GCF. And second, if I think of the factors of 16 and 81, they don't have any common factors. So there can't be a GCF, and if I look a little bit closer, I can see this is the dots. It's the difference of 2 perfect squares, which always factors like this. The square root of 16 is 4, the square root of x to the 4th is x squared, so I get 4x squared. The square root of 81 is 9. Now it said factor completely here, so I'm going to have to factor another time. I only factored once so far. Looking at this one here, this is the sum of 2 perfect squares, which will not factor. This one here is the difference of 2 squares. So the first one will just come along for the ride, this first binomial factor, and the second one we can factor by dots again. The square root of 4x squared is 2x, the square root of 9 is 3, and I've just factored this one completely. Let's see if you can factor this expression completely. First thing I want to do is rewrite the problem and take a look if I have a GCF. This one certainly has a GCF of 5x, so I'll factor that out. Once I factored that out, this is the remaining expression, and I look at what type of factoring remains. This one is clearly trinomial factoring. Now I look for two numbers that multiply to 12 and add to negative 13. Those numbers are negative 1 and negative 12, so I place them in that binomial product. Let's try one final example. See if you can factor this expression completely. This one here I rewrite, and it's a little bit different than all of the other ones. What I see is I have four terms, which should indicate factor by grouping, and you can also see that no common factors exist. If I look at all four terms, they can't have any common factors because the last term, 64, is just a constant, and all of the other terms have variables in them. So because 64 is missing a variable term, and also x to the cube, x to the third is missing a constant term, this cannot be GCF. Well, because it's factor by grouping, the first step is to split those four terms into two pairs. Now take the GCF of each pair. The GCF of the first pair is x squared, and when I divide, I'm left with x plus 4. The second term, remember, needs to have x plus 4 as a binomial. So the GCF here is going to be negative 16, which leaves me with x plus 4. Now group those binomials together by factoring out the x plus 4, and I get this. Remember, it says factor completely, and I've only factored once so far. All of those steps were just grouping, and I have to factor again. I have to decide what type of factoring exists. Well, this piece here is going to be the difference of two perfect squares. The square root of x squared is x. The square root of 16 is going to be 4. When I look at the options up here, none of these appear. But what I notice is that x plus 4 here appeared twice. Think about if you had 5 times 5, you could write that as 5 squared. Or 10 times 10 could be written as 10 squared. The same is true down here. X plus 4 times x plus 4 can be written as x plus 4 squared times x minus 4. Looking at the answer choices, that is choice D. Well, that's it for this video, and that's it for me. I hope in this video, not only did you learn how to factor completely, but also learned how to look at polynomial expressions and decide which method of factoring to use. Until next time.